Okay, people, that happens to be 5 minutes slow, so we'll have to start sometime. 5, 7, 4 more. 2 people are definitely coming. Okay, okay, one is here, 3 more. When we need to start, we are already 12:03. We are at 12:03. Okay, people, welcome back. Let me open up the. Am I getting responses? Yeah, accepting responses. Open up the incentive. Yep, done. So 10 minutes, 11:59 it says there. So 12:09 in that clock, or 12:04 is the correct time. So 12:13 we will finish. Correct time. Five minutes is good, and 5 minutes is mostly good enough, but just in case. Okay, people. Any questions, comments about anything that you want to ask? 2 exercises. We are starting our presentations next Monday, right? This class. So the schedule is also available on your Moodle site. You can check that. Date-wise schedule is available. Please send me your material before your presentation, and preferably the previous evening. I need your presentation, your papers. Yeah, that's all I need. Yeah, you can share a drive or something like that. That should be fine for the papers. The presentation can be there, or you could send it to me by email. That is for the presentation part, and the leverage RS exercises are due on 26th midnight. Okay, 26th April midnight. There are some writing resources that are available, presentation resources that are available in case you want to use them. That's there on your Moodle page also. Remind me, I'll have to give you access to check your plagiarism, turn it in. It will be the same as last time. I mean, the people who took the transport course will already know it's the same thing that I use for all courses. The others, I'll put it up on the Moodle page anyway, so that you can go click on that and check. And for your leverage RS exercise, I'll preferably need one report with your report in front and your plagiarism complete report at the back. No receipts alone, or no something alone, and so on and so forth. I need the entire report. Okay, so please send that. Any other questions? Okay, so that was our last incentive. I mean, reading incentive and so on and so forth. This is the last week. We have only one class left. The last one would be an overview kind of a thing. In this class, we will talk about the scalable reactive species module. I am going to tell you some sort of a history. In fact, I had to prepare for this lecture because the material became available only a few months ago. Prepare the entire lecture fresh, otherwise I normally improve the earlier lectures. So the earlier efforts, they began from 2009 onwards, as I may have mentioned. 2008 I finished my term as the head, first formal head, setting up of the department and so on and so forth. And then I think I had other assignments also, but I started thinking about getting back into research full time. Teaching was always there anyway. So I had started thinking about it, although there were no, it was more of periphery work as to how should we go about it and so on and so forth. The idea was to set up something that anybody can use. We were looking at a website that anybody can use to check the effects of reactive species on their systems. That was how it all started. Then from 2013 onwards, when I think I finished my SAFE headship in 2013 Jan, after 3+ years, and yeah, 3 years plus there was some 4-month they asked me to go on for 4 more months because the next person was not ready or something like that. So it ultimately turned out to be Jan of 2013. So from that time onwards, it was heavy this. A lot of dual degree projects were done, BTech projects were done in this area. The topics were something like this. I thought I'll put some topics and the people who did that. Kinetic analysis of reactive species in a cell, dynamics of reactive species and their effects on anabolic pathways. Both of these had A K Suresh, my previous collaborator, as the co-guide. He was there, we were here, we were doing some online meetings, Skype meetings at that time, and so on. Then next year, a scalable model to quantify the effects of reactive species on metabolic enzymes alone. Effect of induced reactive species on metabolic aspects of Rhodococcus, because Archana was working with Rhodococcus, then we wanted some background thing to be done on Rhodococcus to improve lipid accumulation. Soumya did it. Then these two are BTech students, understanding the effect of reactive species on NF kappa B regulatory module. In fact, some between 2009 and 2013, a lot of work had gone. The BTP and DTPs were looking at disease-related pathways and the effect of reactive species on them. It started a little early. It started in 2006 itself, so they were continuing. So this was more of a continuing effort, but somewhat related to these. So understanding the effect of reactive oxygen species on the NF kappa B regulatory module, more related to this. The other one was directly in disease pathways, mathematical modeling of the genetic pathways of MAP kinase signaling in the cardiovascular systems. Okay. So all these work was going on, and the approach for all this work and some of the previous work was dynamic modeling, which was, if you understand the term, differential equations based modeling, okay, which essentially means it was similar to the RS rhythm cancer model that we saw earlier, Uma's work. To very briefly give you an idea, this was the network that she put together based on information in the literature. So all these are curated informations, all these are actually available, I mean they are not predicted, or they are not guessed, they are actually existing reactions. She put them together in the path of in the form of a pathway which makes sense. That was Uma's work. And then a model was written, essentially mass balances on the various molecules that were present there, right. Those mass balances gave this. This will become a little better understandable in a couple of slides later. And then the rate models for each of these reactions were written down, and they were simultaneously solved to get the profiles of time profiles of the concentrations of the various species. So that was a standard approach, and this approach was fine for our objective for this paper, but for the larger objective it was very iffy. It was fine for whatever you chose, but there were so many things that were unknown and so on and so forth at this level. Okay, so that was not very appropriate, we felt. So we kind of upped the effort towards the middle of the last decade. The effort towards scalability, essentially to improve the scalability, it can be applied to anything, was how to represent the effects of reactive species on enzymes as well as substrates. These are the only two things that are there in the network, and therefore how does reactive species affect any of each one of these, and then can we scale it up. That was the whole idea, and then can it be generalized. And Omkar, who actually did it as a special project, he was not my BTP, he didn't do his BTP or DDP with me. I think he went abroad and did his DDP, but he was interested in the work, and therefore he put in a lot of effort. He kind of put the various things together, and therefore I should mention his name in the efforts. It didn't yield fruit, but that's a different aspect in the large scheme of things. A lot of work went into this. So I'm going to present a few of his slides. Now before that, people who have done transport will know this. We have done this in transport. If you take a network, let us say S naught going inside the cell as S, splitting up into A, B, and then A coming out as C, or B, not A coming out. A gets transformed to C and it gets out, B gets transformed to D and it gets out. The rates are R0, R1, R2, R3 and R4 of these various different individual reactions in the network, and this is the cell which is our system. If you write balances, okay, and these rates are called fluxes for historical reasons, there is no area involved here, but just the rate is actually the flux. So, while writing the material balances for the intercellular metabolites, we consider the intercellular space as a system. For the extracellular metabolites S naught, C and D, we will consider the extracellular space as a system, because that works well. Otherwise, it gets very confusing. Writing the negatives becomes confusing. So, if you do that, this is the balance for people who did not do the transport course. Input rate minus output rate plus generation rate minus consumption rate equals accumulation rate of a species in the system, right. So, this is what is being written for each one of these species that are here. For the intercellular metabolites, we take the intercellular space as the system. For the extracellular metabolites, we take the extracellular space as the system. As you know, the relationships do not matter. The validity of those relationships do not matter, whatever the system you choose. Okay. So, if you write a balance on S, you can figure out that RO minus R1 minus R2 is ds dt. Similarly, you write balances on the various metabolites, intercellular, extracellular, and this is a set of equations, the material balance equations that you turn up with, right. So, these are all the rates that are there, which are called fluxes, and these are nothing but material balance equations, totally consistent, totally complete. There are no assumptions here. So, these balances can be written as a compact form. That was the reason I wrote them separately in terms of matrices, and therefore, it can be scaled. It does not matter how many equations you have, right. So, the size of the matrix and the size of your vectors go up. The mathematical formulation is already there. So, you can just feed it into the computer and let it solve linear algebra problem. It will solve and give you the equations. This, there are no assumptions. If you do metabolic flux balance, then you assume steady state. If you assume steady state, then there is no variation in these with time, the various metabolites. You are taking a snapshot of the cell at a particular point. That is essentially what it means. So, you put all these as 0 and then you do a metabolic flux balance analysis. That is what MFA is. This is complete. MFA, of course, is a snapshot. There are various ways of handling that. MFA is a very standard analysis that is done. Then you put MFA various different snapshots, then you can get a dynamic picture. There is some dynamic modeling, you can bring it into that itself, and so on and so forth. There are a lot of variations that you can do, a lot of improvements that have happened. So, even the metabolic flux analysis is quite helpful. So, in general, stoichiometric matrix times the reaction vector equals the rate of the state vector. So, that is what the basic principle is. So, what Omkar did is he looked at the formation of the substrate from even formation of the substrate, whether it happens or not, you do not know, sometimes it does, from a pool of metabolites. That is what phi means, a pool of metabolites. Then there is formation of the enzyme from a pool of metabolites through transcription translation process, conversion of the substrate to the product, as he assumed Michaelis Menten for a first approximation, and then the product getting either out of the cell or degrading into its constituents and so on and so forth. That is a process. The reverse process is not relevant here. So, this is the system that he considered. This is under normal condition. All these are the possibilities that can happen. What do reactive species do to these processes, kinetically speaking? That is a question he asked. And then he came up with this, the reactive species indicated by the star R here. They could convert the enzyme into another form, which could either be activated or it could be deactivated. Both could happen. And also he brought in the effect of it on the substrate and so on and so forth. I do not think he did the substrate part much, but you could handle the substrate part also. And then, yeah, this is the way he mentioned, he represented this. And once you do this, these become reactions of the system. So, you can add it on to the system, right, and then you solve it, you get the it bring I mean it is essentially the same as solving the set of differential equations simultaneously. So, you have also put in the effects of reactor species into this. That's what we thought might work, but after quite a bit of work, there were just too many unknown constants, right, and we finally had to accept. Sometime in 2016, I think I finally, if 2015 I started realizing that's not going to work. No, 2016 I think I started realizing it's not going to work. 2017 I said this won't work, and we kind of accepted that this approach will not work. Although it's very fundamental and all that, this is not going to work just because of the status of information at that at this time. Okay, just not possible to know all the constant values. Okay, because there are other complications also, which will come about in the next few slides. The constants are determined by individual reactions, right? You do the kinetics of an individual reaction, you find out the constants, and so on. That's the way the constants are found. Keep that in mind. So, at this time, of course, over the past 20 years, things were changing around the world. The relevance of studying single or a limited set of reactions in the context of biological networks, an entire network, was being more and more questioned. They were questioned. It came to a stage in 2015, 2016 when even papers sent for review, the reviewers said, fine, you've shown it in one, what about the others? So, the papers done with one kind of a thing were not publishable anymore. Things had changed, rightfully so, because one individual thing, knowing everything about a particular reaction with the hope that it might work, was not had lost traction by that time. In other words, the 20th century approach, which is essentially finding out individual pieces of information and hoping that they would integrate on their own, was not going to work. Okay. Also, there were other things, other more relevant things in my view, the conditions of study, right. The if you are finding out the reaction rates of individual reactions, typically they are done in dilute solutions. They are not done in concentrated solutions at all. All the regular thermodynamics that you know is only for dilute solutions. All the diffusion you know is only for dilute solutions. We already saw this in transport, that even the diffusivity changes significantly, and you need to bring in the effect of chemical potential. You need to write the relationship in terms of chemical potential rather than in terms of concentration if you have a concentrated solution. So, even the physical applicability of physical relationships was in question. Why? Because the cell is the various materials in the cell, various molecules in the cell are actually in near crystalline state, highly dense, right. And if it is in crystalline state, none of the dilute solution models are going to really work. So, whatever you could rely on for easy analysis were not going to be valid. So, it was going to get totally messy and a lot of other things, and therefore, the individual reactions kind of a view was not going to be useful at all. Once you bring in these aspects, they are not going to be useful at all, and therefore, although it was incomplete at that time, yeah, Paulsen goes to great lengths to say that it is incomplete, it's not fully known, it's only a solution space that you work with, and therefore, only possibilities you can know at that point in time. But all these other things were saying even that is much better than the approach with individual reactions. Okay. So, fine, we shifted our approach. This is the approach that was becoming popular, and of course, Swagatika, Dr. Swagatika Sahu had joined. She was a systems biologist. She started working with all of us, and then I got introduced to this. I took a course and so on and so forth. So, the idea was something like this: if you had read the paper, if you consider only 3 fluxes, okay, V1, V2, V3, there could be hundreds of fluxes, but you cannot represent them in a 3-dimensional space. So, I am limiting it to 3. You add various constraints, it has to obey thermodynamics, it has to obey kinetics, it has to obey various other mass balances, charge balances, and so on and so forth. Then the if you follow the earlier view and the earlier view was indeed true, then you will get a single point. Then you will get a single set of values for V1, V2, V3 which would be valid, we are all happy. But that is not possible here. Here, I mean, you get the single point, but whether you can really apply it to a cell is a big question, right. So, this approach you can apply it to a cell because all the information comes from that space without really knowing the basics of that space, not very easy to know. So, various constraints constrain the space in different ways until you come to a certain region where you find the solution. Okay. And then you could do some sampling to at least get a distribution of the possible solutions that are there. Very computationally intensive to do, but at least you can get a distribution, therefore you can get an expected value and so on and so forth. That is the best that you can do as of today. Okay. Even this is quite recent in terms of people doing it. This was known in 2019, I mean even earlier, but people doing it because this is highly computationally intensive and the algorithms do not work very well, available algorithms do not work very well beyond a certain size of the metabolites and reactions and so on and so forth. Subhashri had major difficulty in making her sampling work for 3000 reactions. No, hers was more. Till about 3000 it works fine or something like that. So, at this point in time I had an idea that if it is brute force, I saw it always as a brute force thing because you get some region, no elegance there, put everything and then crunch. I still hold that view, but that's the best that we can do. Said fine, we take all the reactive species reactions, feed them into the metabolic system or have them as a module, integrate them into the metabolic system. Thereby you will know the effect of reactive species on this. In terms of your network, it is just adding few more, right, does not matter. And this is the basis for the solution with systems biology. Your flux balance analysis, flux variability analysis, you start with flux balance analysis. Okay, you get a set of fluxes that you work with. If you have already done the course, you will know that that's the best that you can do. You cannot get concentrations, and time is, you will have to struggle to get time. Okay. So, can we do that? Swagatika said, yeah, that's a fine, that's a okay approach, there's nothing wrong with it. Good, then we got into it. I thought we'll be done in 2 years because there's this NIST database which is so big, everything we'll know and so on. So it took 6-7 years after that, and a lot of DDPs who worked on it. All of people who contributed enough are definitely acknowledged, and some of them are authors on the paper. So yeah, so the idea was add the set of reactive species reactions as comprehensively as possible to the relevant metabolic network. In other words, have a module integrated with the metabolic network was our idea. In this case, scalability is guaranteed. It adds on to the stoichiometric matrix or the matrices that are relevant. So we are done, no problem. So the module development consisted of these 3 steps, which Prerna and Subhashri oversaw. We consulted various databases such as NIST, NRDL and so on and so forth to get the basic reactions. Each DDP did one set of reactions, okay, ROS, RNS, RSS, and that's how the DDPs and BTP, no DDPs then, no BTPs then, DDPs contributed that way, and then they were manually curated. Okay. There are reactions, but the information is not complete. What is the effect of pH on it, what is the effect of temperature on it, and so on and so forth, all that was not known. Are the charges balanced, that is not known, and so on and so forth. So that is what took time. Reactions were manually curated, which took many years. Then we completed the large number of incomplete reactions, verified mass balances, verified charge balances, removed thermodynamically infeasible cycles that also arose, not the only reason, also arose due to improperly included reversible reactions, and various different available softwares were used on it on Cobra. And to incorporate the improved RS module into the needed genome scale metabolic model on the Cobra platform, we used various programs. All our programs are available on this link. The link is available in the paper. You can download it and use it anytime. Okay. Just acknowledge us. So, this is how the what Subhashri did. Okay, the story went something like this. We did this, and then Prerna was overseeing it, and at that point in time the focus was on drug discovery. Okay, so we showed how drug discovery is better with, or possibly better with, the RS module and so on and so forth, and sent it to computational biology. Very good journey. They didn't like it. They didn't like the fact that these two aspects were put together. By that time, Subhashri had gone for the Cobra conference. There was a lot of interest in the RS module alone, but somehow putting them together was a bad idea. So, it is still a bioarchive paper. You can go and read it anytime. Then we completely changed things. Subhashri took over. She was working on cancers. We said, you just look at the RS module, make it complete, apply it to cancers, and show that this works better than, this predicts better than your metabolic networks or your genome scale metabolic model without this RS. So, it was kind of a very focused paper. That went through in metabolic engineering in a straightforward fashion. So, to develop that, she needed data, she needed a generic model which was Recon 3D, and a lot of algorithms. So, the requirements of building the 3 cancer cell line models, and the how she went about, or we all went about, putting the or integrating the reactive species module along with the genome scale metabolic model as given here.